What's up, people? We're about to start the lecture. Alright, welcome to the Move Semantics lecture. Let me switch the screen. Alright, hope you can see it correctly. So we'll be covering Move Semantics, which is a way to avoid costly copy and forward arguments to functions. We'll first see use cases where this could be useful, and from there we'll see how we can fix some code that's doing a copy for nothing. I'm using Godbolt, which is an online compiler. On the right you can see the assembly output, but we don't really need that. You can also see the program output, so that will be really useful. So we'll start with something like an image class, which contains some kinds of image data. And we can imagine the image data is something big and has a lot of data and takes time to copy and everything. So we'll have our image data pointer. And when we are constructing this class, we'll just create a new pointer for this data. And so that's good. We can go ahead and create one image. And of course we need a destructor to destroy the data. Okay. Little typo. Everything has to be public. Very good. So now we have a image object which, when it is constructed, it initializes this structure is a lot of data, and when it's deleted, it destroys it. And now maybe we want to have another image, which is a copy of the first image. But for that, we need a copy constructor, because currently what it will do is just copy the data pointer, and that will destroy twice the data, which is pretty bad. So we'll go ahead and make a copy constructor. Sorry, one sec. Okay. So now we're copying the image, and that's kind of a costly operation. So sometimes you do not want to do a whole copy, you just want to hold a reference like that. And that's better if you actually going to use the same image and you're not going to modify it, or if you're going to modify it but you also want to modify the first image, you just want to hold a reference. And if you're not going to modify it, you can hold a const reference to the first one. Okay, that's great. So now we arrive at, oh, let's also define the assignment operator bit, because maybe we have two images and then we want to assign back not our first image to image 2, and for that we'll need the assignment operator, which looks a lot like the copy constructor, but we first have to make sure to delete our data if we have any. And that's compiling. Okay, so that's working. But sometimes, so what's going on here, for example, is that it's going to create a new image. It's going to here to copy all the data, and sometimes you know that you're not going to use image again. So in those cases, you'd like a way to tell the compiler, hey, just take the data that's in image and put it in image 2. I don't want you to I don't want you to create new data. I just want you to reuse the same data. And that can happen, for example, if you have a function that's returning an image, you know, and it's returning it, and you don't want so you don't want, so the value is going to be returned by make image. You don't want it to make a copy and then assign it to image and then delete what was returned by make image. Yes, do have a Canadian accent, did you? What you'd like is just to move what's inside what's returned by make image directly into image. And for that, basically, C++ provides a new type which is called R-value reference. And what an R-value is basically a temporary. So what is returned by make image is a temporary. At the end of this lane, at the end of this expression, the temporary is going to be destroyed. But at this particular moment in execution, it exists. And the difference between a reference, which is a normal reference called a L value reference, and a R value reference is just made with those two end symbol, those two ampersand. And so all we have to do if we want to make a new constructor but that takes a R value reference is use those two ampersand, and all it does is make use function overloading. So see, if you pass it R value reference, going to call this constructor, and if you use a normal reference or R value, is going to call this one. And what we want to do basically is assign our data to the other guy's data. This way, this way we are directly taking his data. Since we know that the other guy is not going to use it. Oh shit! I didn't put this on the right line. Sorry, this is meant to go remove constructor. So since we know that the other guy is not going to use that data anymore, we just take it and then we tell the other guy, you know how have no data, just no. And basically here this should be initial picture. So this is basically a swap, right? Our data is null and we're taking his data and then we're assigning it null operator. So what we can do is simply swapping the two value using std swap, and that will simply swap the content of both variables. Let me actually use correct C++ syntax here. Yes, John, but we're trying to be really explicit here. So John notes that when you call delete on a pointer, if the pointer is null, the delete will do nothing. Here I'm putting it explicitly because I want to make everything really clear. I don't want to have I want everything to be explicit so everyone understands correctly. Just for the tool. Also here we're using raw pointers, and I want to note that you'd probably want to use small pointers, in this case probably a unique pointer, so that you don't have, for example, to manage this deleting the data yourself or calling new, which in C++ you shouldn't have to do really often, in modern C++ that is. So now we're initializing our data, and what will happen is we're taking its data and his data is getting to null and everything is fine. We didn't have to make a copy, so previously we were making a copy of that data. Now we don't have to do that, and we can also make assignment operator, because imagine we already had our image variable, and then we just do stuff with the image. Oh my god, I can't write. And then you want to assign it. Now we are, again, this is a temporary. We don't want to copy it. We want to move it in image. So we're going to make our assignment by our value assignment. Sorry. So here previously we had to check if we had any data, and if we had any, we deleted it, and then we copied the old data to our pointer. What we can do here is again simply do a swap. So our old data will now be in the other guys. So if we look at example of this line, the data was previously in image will now be in the temporary that was returned by make image. And so we don't have to delete the data ourselves in this operator, because when this temporary will get deleted, it will contain our old data, it will call its destructor, and it will delete the data. So we don't have to manage that here. So that's the basics of how the move semantics works. It's simply a way to say, hi, compiler, this is a temporary, so I'd like to do something different, or that I don't want to do costly operation. I know since we won't be reusing that variable soon, I will just directly take its data. When you move from an object, so here basically you're taking stuff from this object, the standard says, no, DG, this is the way to go. So the standard says you should leave the variable you moved from in a valid state, in a valid but unknown state. What this means is you can still use that variable. So let's say we have two images, image 1 and image 2. Now you have done some stuff with image 1, you have done some stuff with image 2, but now for some reason you want to assign image 2 to image 1. And you know that until the end of the function you won't be using image 2 again. But image 2 currently is not a temporary, so it will call the normal copy assignment operator. So what we'd want to do is tell the compiler here, hey, this, we're not going to use it again. So please move it, I want to move. So for that we have stdmove. And all stdmove does really, all it does really is convert this to a value reference. It's just a cast. Casting this L value reference to a R value reference. And since it is a R value reference now, it will call our move operator. So now, with our particular implementation, image will contain the data that was in image 2, and image 2 will contain the data that was in image 1, but that's just because of the way we did it. You could do the move operation in many different ways depending on the way your data is. So now you might be wondering, so you moved image 2. The stdmove itself, this function, didn't do anything to the variable. All it did is make it a R value reference so that you can get the proper overload. But what's the state of image 2 now? And what I was saying is it's still a variable you can use. You can still use image 2. Honestly, if you're moving from a variable, you probably don't want to reuse it. Reuse it can make the code a little bit confusing. But for example, with vectors, so let's say for a second, instead of image, we had vectors, because vectors actually have function. So I can make an example. Is it going to work? Okay, so now let's say you use vec1, you use vec2, fill them with stuff, and now you want to set vec1 to vector2, but you know you won't be using the data that's inside vec2 again. It's bye-bye. Now, what's the state of vec2? You can still use it, but you don't know which state it is in. So if, for example, doing this would be bad, because you don't know if there's an element. You don't know if you can access the first element. Even if before this line here there was elements in vec2, you don't know if there is any after the move. But you can call .size. You can call function that check the state of the variable, or you can call function that set the state. So for example, clear. To call clear, you don't have to know what was the state of the variable before, and you know what the state of the variable is after. So this is perfect. After that, you could use vec2 normally, because now you know which state the vector is in. It's empty, and you can set stuff in it. So that's it for the std move. All it does again is make a value reference with your variable so that it calls the proper overload. And that's the gist of it. The std move itself doesn't do the job. It's the different overload I would call that does the job. Also, even if we didn't have like those, the assignment, the value assignment and the value constructor, you still can move it. It's just that it will call the normal constructor or the normal assignment operator, and it won't change anything really. Let's see. Just looking at my notes real quick. Yes, let's look maybe a little more at the value itself. So if I have an int reference, let's say I just have an int called foo. Let's initialize it because we're good mans. And now I have a reference. I can set it to foo. What the heck? Yes, okay. You can set it because foo is an L value. It's not a temporary. It's here. So you can set a reference to this variable, but you cannot take a reference from an R value. So here in this case, 0 is a temporary. It only exists for this expression, and after that, it doesn't exist. Will get destroyed. For example, if we had a function that makes int, I'm using int in this case because it's a simple type. Just to because I want us to only think about reference and values. So here the same thing happens if we try to assign a reference to the return of make int, because make int will return a value. It's just returning a value. But this value is temporary. It only exists from the return of the function and won't exist after this line. But you can use a const reference. This is like a special rule in C++. You can assign a const reference to a temporary. And this, because usually the temporary will die on this line, but this will extend the lifetime of this temporary to the lifetime of this bar. So this variable, this const reference to an int that's called bar, will stop to exist when you exit the scope of main. So here, bar stops existing. Normally, the return value from make int, which is a temporary, will stop existing on this line. But since we assigned it to a const reference, it will actually stop existing on this line. It will die with bar. Someone licked me some shit. What do you want us to look at exactly, Alex? Okay. Some people arguing about C++ specifics or about the lifetime extension. I actually don't know the exact details. I don't remember, but that's like the gist of it. Okay, so we can assign a reference. We can take a reference from a value. So remember here we're returning a value, and we can also take a value reference. Can we? Yes, of course. Because this means, okay, this is a temporary. A value, basically, that's what it means. So that's what I wanted to say, basically. Also, you couldn't take a pointer from this, because it's a temporary. Yeah. And that's a quick rule of thumb to know if something is temporary or not. if you can take a pointer from it, so if you can use this operator, it's a L value, and if you can't, it's probably a R value. So I cannot take a pointer to the value that was returned from make int, since it's a temporary. So we know it's a R value. Let me check my notes real quick. Okay, we covered that. Okay, so now stuff start to become a little bit weird. So let's say I have a variable that takes this a function that takes this R value reference, right? And it's just casually taking first R value reference. Now, what happens if I call it with a temporary? So it works. Well, just comparing, yeah. So it works because this is taking a R value reference. Now, what happens if I try to take the address of foo? Wait, give me one sec. Yeah, so like here we can actually take a pointer to foo, but it's a R value reference. What's going on? And the truth is, even if you have a R value reference, it doesn't mean that the actual variable, when you use it, will give you a R value reference. Shut up, Peter. Yeah, sorry, I'm looking over my notes and my notes, and they're not really well made. It's like an old presentation I gave once. Yeah. So if we come back to our image class, this will make it easier. If I can manage to write image. Okay. And we have our old make image class. Okay. Let's call this take image. Okay. So here we have an image. And damn it, I really make a lot of typo. Okay, so let's go back from the basic. We have make image, right? That will return a temporary. This temporary is passed to take image, and take image takes it as a R value reference. So far, so good. Now, what would happen if we want to make a second image here from a first image? And what you could normally expect is, since this is an R value reference, you'd expect this to call our R value constructor, right? But it's actually calling this L value constructor, because image here, when you use it, has a name, and basically everything that has a name is a L value. That's like some weirdness of C++. If it has a name, it's a L value, and if you want to take R value from this one, you'd have to move it, because even if you took it by R value, it now has a name, so it's now R value, L value, my bad. And that can be pretty important, because if, for example, in our class image, we'd be taking some other type, Let me actually copy this whole thing so you can see it. So I'll just remove those. Okay, so let's say you have a class base which has like a normal L value reference constructor and a R value reference constructor. And now you have another class that's deriving from base, and that constructor, you want to, if you call that derived constructor, you want to call its base constructor with the L value, and if you call it from R value, you'd want to call it from R value. But here, since this has a name, even though this is a R value reference, since other here is the name, you're actually calling your base constructor from L value reference. It's not calling the temporary overload. So you'd have to move it because the return value of move here doesn't have a name. So it's returning a R value, and it will call the correct overload of base. And this is a common pitfall. So even if you take stuff by R value reference, you still have to move them because they now have a name. That's like a little note you have to make here. So yeah, the example Storm is asking. Well, let me check something real quick because I didn't actually check the Mixer chat. Yeah, maybe you should return, but it's fine. So Storm is asking why move semantics would be useful, and for example, this image class is a good example. You have this costly image data that's taking a lot of time to copy, or is big, or you'd want to avoid. Maybe it's just because you have to load a file from the disk, which takes a lot of time, or you have to do many steps to initialize it, which takes a lot of time. And when you're constructing this class from from an R value, so from a temporary, you don't want to have to copy the whole data again, or have to reload the whole data again, or initialize it again. You just want to steal the data from the temporary. For example, here we did that by simply swapping the pointers. The same on the assignment operator. Move semantics. So yeah, I was also going to say, in some case, here I get into templates. Might be unfamiliar for some of you, but it's part of C++. So sometimes happens in C++ that you want to call. Jesus. Sometimes you want to have some kind of callback, or you want to pass a pointer to something, and then call multiple arguments to it. And that happens in, or maybe actually I can just give it with an image. No, that won't work. Okay. So sometimes you take a functor is like something that you can call. It's like a function, and you want to give arguments that should be called on this function. And it would looks like something like this. For example, if we have take image, so here what I'm saying is, let me just actually implement it. What I'm saying is, take image, which is the function. I'm passing this function to call functor, and I'm also passing make image. So I'm telling it this function will call take image with the result of make image. And this is something that happens in C++ from time to time, where you have to this kind of pattern. And one of the issues here, I'm even getting an error, is that here this function takes a R value, but this function and this function returns a R value, but this is taking the arguments by copy. Wait, is it? Oh no. Well, it has a name, so it's not doing the. It's L value. So you cannot call take image because this is going to be a L value, and that was a issue before in C++ because what you had to do is either take a reference, but then wait, but then that wouldn't work well when you pass a temporary like this, or you take a const reference, but then when you actually wanted a simple reference, it won't work. And C++, I don't know, 11 I think, introduced std forward, and what it does is basically it forwards the argument. You use it when you want to pass the arguments you've received exactly like you have received them. So I received args with some of the arguments might be R value, some of the arguments might be L value, and I want to pass them to the functor exactly like I have received them. And this is what std forward will do. If for each argument, if it's you have received an R value, it will forward it as a R value. If you have received it as a L value, it will forward it as a L value. And this allows us to have to be able basically to call or take image with make image. So this part might be a little bit confusing if you haven't seen templates and variadic templates, but we'll get to that in a next lecture, I think. Another rule in C++ is the collapsing of reference. So here, let me delete this. I will be using so for people that don't know, image is using is a way to alias a type. So when I will use image ref, it's like now a new type, which is basically just this type. So I can use image ref. So let's say I have image 1, and with my everlasting typo. Okay. So image 2 is now a reference to image 1 because an image ref is image reference. It's the same as using a type def, but the syntax is nicer because in type def it's kind of reversed. It's like you're declaring a type, and it always makes me confused. It's all C++. Also, using can be templated, so always use using instead of type def. Okay, so now let's say I have image ref, and someone for some reason, because with templates sometimes you don't know what the type will be coming, and now someone does this, and this basically, if you wrote it out, would be an image reference and another reference to image 2 or image 1. Okay, like this. This is what it becomes, right? Because image ref is image reference, and then you have another reference here. And what happens in this case, you cannot write it literally like this. It only works when you have like types aliasing and stuff like that, or templates. What it does, it is collapse the reference, because C++ doesn't have the concept of a reference to a reference. That doesn't make sense. So it will collapse the reference and will basically become just a reference. Now, what happens if you have a reference to a value reference? It will again just collapse it, and it will become a simple reference. The collapsing rules is basically if you have a mix, if you have two normal reference, it just becomes a normal reference. If you have, let me write it up here. If you have a reference plus a reference, it becomes a reference. If you have a reference plus a value reference, it becomes a normal reference. If you have a value reference plus a normal reference, it becomes a normal reference. The only case where it becomes a value reference is when you collapse two value reference together. So if this was a value here and we have another one here, then this will actually be a value reference. And as you can see, actually we cannot assign it here because this is not an R value. This is an L value, it's not a temporary, it has a name. So this is not, you cannot bind a value reference to it. But as you can see, if we just had one, it's going to collapse the two type of reference to a normal reference. This is the case, this one. It's going to collapse to a normal reference, and this will be like just a normal reference. Yes, I am really struggling to type image every single time. The reason why I was bringing reference collapsing is because in C++ you have the concept of universal reference, or I don't know if the no, it's R value reference, R value, sorry, or L value. So I'm not sure actually if this is still the name of the thing, but it's called an R value reference. And the difference, a universal reference, my bad. And the difference is just that it's an, let me move that here. So a universal reference is when you have a compiler deducted type and then the double ampersand. So what is a compiler deducted type? It's basically either auto, which will like deduct the type from the assignment, the context, or you have a template. So when using template and you have a type name T, for example, T will be a compiler deducted type. And then if you have the T and then the double ampersand, then this will be a universal reference. We'll use auto here because you can just use it in main, it's easier to see. And so what is going on here? Because this is a L value, this is not a temporary, this has a name, and we're assigning it to a universal reference. And basically what the universal reference does is if you assign it from L value, it becomes a L value reference. So it becomes just like a normal reference. But if you assign it from a R value, if you move it, for example, so this is returning a R value. Why is it not? Oh, we just mark it. Okay, we're just missing the parentheses. Oops. So if you assign it from a R value, it becomes a R value reference. So that's what the universal reference is. If you assign it from the L value, it becomes a L value reference. If you assign it from a R value, it becomes a R value reference. And this can be confusing if you're using, for example, like auto, and you might think you're assigning a R value, but oh, actually, no, this is a L value because this is a deducted compiler deducted type. This is a universal reference. It's not simply a R value reference. So you have to be careful with that. If you just type the type directly. This is not like compiler deducted, so it will actually be what you expect. So here we cannot assign it. But when you have templates and auto, you have to be mindful of that. Let's see, we'll have other slides. So when you have the move constructor and the move assignments, it's important to be mindful of exceptions. So here, for example, this function won't throw an exception, so we can mark it no except. Oops, if I can type it correctly, no except. Yep. Is it going to accept my code? Did I make a typo? No except. And thank you, John, here. I obviously cannot type in C++. And here, too, is just a swap. No exception is going to come from that. Because this could throw an exception, okay? You could be out of memory. You could be this particular variable, when you initialize it from whatever, from the copy, might throw an exception. You might be handling this, but here we're not, so we're not going to mark this no except. We don't know what could happen. But here, this is a swap. We know this is going to happen. This is not going to fail, and same with this one, so we mark it no except. And the reason why it's important to mark them no except is because for example, when you have a vector and you decide to resize it. Okay, let's say I have a vector of image. Vector of image. Yep, still can type images. Okay, and you decide to to resize this vector to 1. So this here, the vector will have to initialize or image variable inside the vector, right? We'll call the constructor. Now let's say we resize it to 10 later. Now the vector has to allocate new memory and move our old data to our new data. And if we didn't have any move, semantics in our class, it would just call the copy constructor. Would call this on the new location from our old location, and then we'll delete what was at the old location. You cannot really see this from this code. This is behind. It's in the vector implementation. But if you have a move constructor, you have to have a move constructor. It will call the move constructor, but only if it's no except, because in the way that the vector resize works, it wants to make sure that the data ends up in a certain way, and if it was to move it and there was an exception in the middle, it would mess things up. So it will only use your move constructor if you mark it no except. So that's why it's important. Many containers in the STL work this way. You would gain performance and you do what you want, but you have to remember to make it no except. Otherwise, it won't use it. It'd be like, nah, this is too dangerous. I won't risk it. Let me see. I think let me just check again my notes. Yeah. So also, like, there's things that you don't want to move. For example, you wouldn't move an int because there's no special way you could move copy an int to save memory or time, for example. Int is just an int. You just copy it. There's no point in moving it. So not all class will benefit fit from moving. Again, if you have some data that is expensive to compute, expensive to copy, expensive to initialize, you might want to think about the move semantics of that class. But otherwise, it's not often going to be needed. So for example, the strings or vectors have move semantics because when you assign a vector from temporary, you don't want to copy the whole vector data. You might have a lot of data in that vector, so you can just exchange the data between the two vectors and take it from the temporary and put it in that vector, and that's where move semantics really becomes useful. So maybe I'll just do a quick recap, and then we can end on that. Yeah. So move semantics works on overloading functions. It's just a way to overload functions so that you can say, oh, this is a temporary or this is a variable I want to move on, so please call this overload. This is the overload for I just want to copy from this function, from this variable. This is the overload for, oh, I want to move from this overload. And you can tell the constructor that you want to move from a variable by using stdmove, and all it does is cast the reference to our value reference, so we call the correct overload. But stdmove by itself doesn't do anything to the variable. Okay. Another thing is if you move from a variable, so if you moved from images, we'll just actually do it. Move images. So if we move from images, we don't know what the states of images 2 is. We know it's a valid state, so the variable can still be used, but we don't know if it still has elements. We don't know what the elements are. We don't know the size. But we can call functions that don't assume the previous state. So for example, images.clear is fine because it doesn't assume a previous state. It will just set the state of images. But images dot and like taking an element or something, this is not okay because we don't know if there's an element in it or not. We have to remember always make our move constructor, move assignment, no except if we can. And there's a std forward that can be used. Probably, maybe we'll see it again in the template lecture, the template variadic templates lecture. But std forward is a way that when you want to pass arguments that you have received to another function, you want to pass them exactly as you have received them. So if you receive the L value reference, you want to pass L value reference. If you receive the R value reference, you want to pass R value reference. This is the way to forward the argument, to pass it exactly like you have received. We've also seen that sometimes things not like they seem. Even though this is declared as a R value reference, the actual variable image that is the reference when you use it is an L value reference because now it has a name. So if you want to use it as a R value reference, you have to move from it. You have to use stdmove. We've also seen reference collapsing. So when you have two type of reference sorry, that have been put together, they will always collapse to a normal reference except if both of them are R value reference. We also seen universal reference where you have a compiler deducted type and then the R value reference syntax, but this is not an R value. This is a universal reference because auto is a compiler deducted type. I think that's pretty much all we've seen. Hope you enjoyed the lesson, and I'll see you guys in the chat.